But, you know, we've been working hard on this 4-3, which is a first derivative test, mins and maxes, increasing, decreasing. You know, sometimes these problems are worded a little funny. I wonder if you can, like I assigned this in 4-3, I assigned this 91. Did anybody try 91? Were you successful? It's kind of easy maybe, but again, it's kind of, it says a differentiable function, f has a critical number at x equals 5. So they're telling me I've got some function, but I don't know much about it except it has a critical number at x equals 5. That's what they say. You know, what does that mean? If it's got a critical number at x equals 5, does that mean it's a min or a max? Is that what that means? It's got to be a min or a max? You know, that's not really true. We've probably fallen into that trap. I probably steered you into that trap. You know, a critical number is a good candidate to be a min or a max, but it doesn't have to be. It can, listen, when you do the test, it could be a min, a max, or a neither. You know, what you would do is you would put him on a number line, and you would test him. And we've done this. We've done this a lot. But you know, if it's increasing and then decreasing, then of course it's a max. If it's decreasing and then increasing, it's a min. But there are exceptions. This can happen where it increases and then continues to increase, and then it's not a min or a max. And maybe you haven't really run into too many of those. They are a little rarer. But it can happen, and so then he's I would call him a neither. Okay, he's not a min, he's not a max, he's a neither. You know, visually how that might show up. I mean, how can you have, you know, maybe your derivative, you set your derivative equal to 0. You got this critical number. So how can you have a slope of 0 and not be a min or a max? I'm saying it can happen. Do you know how that can happen? A slope of 0 but not be a min or a max? I mean, there's really only one example I can think of in my brain. It's this. Where you're on some kind of graph that does this, where technically you have a slope of 0 at that point. But is it a min or a max? No, it's not. I mean, does it increase and then decrease? No, it doesn't. It continues to increase. So it leveled off for just a second and had a slope of 0 for just a brief moment. And technically he's a critical number, but when I go test him, my test might look like this. Now hold on, I'm not really doing 91. I'm speculating on all the possibilities of what happens when you have a critical number. It's usually, I keep saying usually a min or a max, and you might have turned that usually into always in your brain, but don't do that. It's usually a min or a max, but it may not be. You know, same with those inflection points. That's why technically we called them possible inflection points. They usually are, but you're not sure if they're really an inflection point until you see if it changes concavity by testing that number line. So that's really the same with these critical numbers. Anyway, back to 91. What it did tell me is it told me this. F prime of 4 is negative 2.5 and F prime of 6 is 3. They gave me this piece of information. F prime of 4 is negative 2.5 and F prime of 6 is 3. Now I'm supposed to use that information and reach a conclusion for them about this x equals 5. And maybe it's easy. I think it's easy, but you know, again, some people just have a hard time reading math. You know, if I did find this critical number, I would put it on a number line and I would test around it. And you know what? That's what they're telling me here. They're telling me if you plugged a 4 into your derivative, you would get a negative number. So into my derivative, I mean, I don't have a function, and I don't have a derivative, but I've got some information. And it says, if you plug 4 into the derivative, it's negative. Well, 4 lives right here. If the derivative's negative, I know the function is decreasing. This piece of information says if you plug 6 in the derivative, it's a 3. I don't really care that it's a 3. It's positive is what I'm really focused on. So that means if you plug a 6 into the derivative, it's positive. And so it's increasing. So this information is just kind of to help me do my number line, I suppose, or do my first derivative test. And I've reached a conclusion. X equals 5 is a relative min. And I'm finished with 91, which I would call kind of an easy question. But it was kind of more conceptual. You didn't have a function to work with. You just had some information to work with. There's a 97 also that I kind of like the look of. Sort of. Let's try this 97. So I'm kind of doing some homework for you or with you. 97 is kind of complicated. I might skip some of it. I'm in 4.3. It says that you have a function called c of t, and it is 3t 27 plus t cubed. 3t over 27 plus t cubed. Okay. And here's what this is. The concentration of a chemical in the bloodstream T hours after injection into the muscle. Wow, okay, into the muscle tissue. So this might be good for healthcare workers. What are we saying? That C of T is the concentration of a drug in the bloodstream, and T is the number of hours. Okay, all right, so now I understand what the function is. Here's what they suggest. They want me to fill in this table. So they want me to plug in 0 and 0.5 and 1 and 1.5 and 2 and 2.5. They want me to build a little table to see some of the y values. I guess if I look at a table of y values, x and y values, or t and c values, if I look at a table of values, I could see when it's the most concentrated, when it's a max, I guess. I'd rather not fill in that table. In the interest of time, you could try that. Part B says this: use a graphing utility to graph the concentration function and approximate the time when it's greatest. So you could use a graphing. I'm going to skip this too, but you could use a graphing calculator. Type this in. Be careful. Use parentheses, and maybe you can see, when it's a max. That's kind of what they're asking. Then finally, part C says use calculus to determine when it's a max. So I think I'll do that. You following me? They wanted to make a chart and plot a bunch of points to see when it's a max. Pick up a graphing calculator and see when it's a max. Or finally, just use calculus to see when it's a max. And how do we do that? Take a derivative. Set it equal to 0. Look for your critical number. Perhaps that critical number is the max, but perhaps you should test it to see if it's the max. All right, let's just do that real quick. I'm going to do it real quick. Maybe. The derivative is a little quotient rule. I almost got sick of quotient rules the other day, but not quite yet. I still love them. The derivative of the top times the bottom minus write down the top and take the derivative of the bottom, 3t squared, all over the bottom squared. You know what I mean? A good old quotient rule. That's the derivative. I'm going to distribute and clean up that numerator. That's kind of where all the action is. That's an 81 plus 3t cubed. Minus, that's okay, 9t cubed. All over this denominator. Squared. Hey, if I want to know when this equals 0, then I would set the numerator equal to 0. By the way, I can combine a couple like terms there. But I'm going to just set the numerator equal to 0, looking for a critical number. That is an 81 minus 6t cubed, isn't it? Is that what that is? So I'm setting the numerator equal to 0. I'm going to find this time using calculus. I mean, again, I could have done a chart like they wanted me to. I could have used my graphing calculator like they wanted me to, but this gets you exactly where it is right here. I think I'll move the 6t cubed over. I think I'll divide by 6 and take the cube root. The answer is, hang on, that's 27 over 2, I guess. That's 27 over 2 is what that is. Anyway, t is the cube root of 27 over 2. Because this is sort of a word problem, perhaps a nice decimal would be appropriate here. By the way, what else? The cube root of 27 is a 3, and the cube root of 2 is, I'm not sure. But there it is. There's your critical number, a little more simplified. But I just asked for a decimal. What did you say?
2.3.
2.38. Is that what you said?
Yep.
All right, thank you. I bet that's when we're a max. I bet that's when we're a max. I mean, it's the only critical number I got. If I had 2 or 3 critical numbers, maybe one of them's a max, maybe one of them's a min, maybe I should check it out. You know, this question was sort of asking, when are you a max? And then we only got 1 critical number. I'm pretty sure it's a max. I don't really want to go prove it to you. How would I prove it to you? How would you prove? Right now he's a critical number. How do you prove he's a min or a max? Well, thank you. You do a first derivative test, right? I don't think I will. I bet that's a max. I think I'll just skip that test. I want to keep going. You got a question, Carlos?
One, yes, over there where you have t equals, you have the square root of 27, half, and to the third root. How did you go from that to what's on the right side of it?
I don't know. I don't know.
To 3 over the square root of 2 was the third root.
Yeah, the cube root of 27 is 3, and the cube root of 2 is cube root of 2. Yep.
Oh, okay, I see.
Let's go. Keep going, doing some homework. If I move to 4, 4, I could ask you for some requests, but maybe I don't want to.
But I have a request.
Well, yeah, but I might not have asked you.
It's a hard question.
So there's these questions. Check out this question. In 4, 4, I want to do this number 70. We haven't got to this yet. There's this question. F of 0 equals F of 2. I assigned a couple of these. There's about 4 of these in a little batch. 69, 70, 71, 72. These are good little questions. F prime of x is greater than 0 for x less than 1. F prime of x is greater than 0 for x less than 1. I'm sorry, F prime of 1 is 0. And F prime of x is less than 0 for x greater than 1, less than 0 for x greater than 1. You see, this is actually a pretty easy question, but it's reading this information and understanding it. You do understand it. You've been understanding it as I do these problems, but what's funny again is you're not given a specific function. You're just given a bunch of information about a function, right? So nobody told me what f was. They didn't give me an equation for the function, but they're telling me a lot of information about the function, and then ultimately they want a graph. They from this information, I should be able to sketch kind of a rough graph. Kind of a rough graph. Some specifics are in here, and then some of it might be rough, some of it might be specific. Are you guys with me? Did you try any of these problems? I don't know if you got to these yet. In 4, 4, up here. We haven't practiced them yet. I like them though. It might show up on a quiz or a test. They're not that bad. Watch. Let's see. So if I just start reading from the top, what's this information telling me? It looks to me like that's an x value, and that's a y value, right? I mean, these are just points. And I think they're saying when x is 0, it's the same y value when x is 2. When x is 0 and when x is 2, they both share the same y value. What is it? 0. So when x is 0, the y value is 0. And when x is 2, the y value is 0. So that's what that, you know, I'm reading math. It's not that hard to read. You're getting better at it, I guess. Hey, these next 3 things I feel like sort of go together. They're all telling me statements about the derivative. And I'd like to focus on the middle one here. When you see that f prime of 1 equals 0, that's telling you that when x is 1 and you plug it in the derivative, you get 0. I mean, when I talk this English to you, I guess it helps. The math is this. And maybe you should talk to yourself like I am. What did I say? Oh, when x is 1 and you plug it in the derivative, you get 0, which means it's a critical number. It might be a min or a max, but all I know right now is that it's a critical number. Right. You know what? That makes me, when something's a critical number, I really want to kind of put it on a number line and test around it. I'm going to make a little number line here. I'm going to put 1 on the number line because it's a critical number. And now I'm going to try to test around it. Well, I don't have anything to test. Well, hang on. They did give me some more information. Look what they told me. When x is less than 1, the derivative is positive. The derivative is positive when x is less than 1. That's what that says. Again, you're reading math. So, hold on. When x is less than 1, the derivative was positive? That's what that says. When x is less than 1, the derivative is positive. That's what that says. You know what this says? When x is greater than 1, the derivative is negative. When x is greater than 1, the derivative is negative. Okay, they're giving me my information I need to do a first derivative test, and I kind of just did it. And I realize that it's increasing and that it's decreasing, and so I realize that he is a max. So when x equals 1, there's a max. Now, where is it? I don't know. They didn't tell me. Okay? This is the part I don't know. I don't know how, but it's a max. It's higher than those guys, I guess. You know, I don't know the exact y value, but it's a max. Cool. What does this say? Wow. It says the second derivative is less than 0. Okay, you can interpret that as the second derivative is negative. You should maybe know that when the second derivative is negative, what does that tell you about the function? When the second derivative is negative, what does that tell you about the function? It's concave down. And did it specify like, oh, when x is greater than 3 or when x is greater than 7? Or no, it didn't. And you know what it means? It means it's concave down always. I mean, it didn't specify for certain x's. It says the second derivative is negative, basically always is what it's saying. So it's concave down. That's what that statement says. So the graph is concave down. F is concave down. The function is concave down. Well, cool. That kind of makes sense. I mean, I got this increasing, decreasing, concave down. I'm ready to sketch a graph, don't you think? I mean, that's all. That was number 70. You can try the others in your leisure. 69, 71, 72, they're all similar. Yes, Carlos?
I still don't quite see what you were saying that when it's 1 to 0, you know, is positive. Where is it? Maybe no. When it's less than 1, you know, it's positive. Greater than 1, it's negative. But how can you tell, judging from the information and giving it the problem again?
Yeah, it's right here. Right.
I just don't see it.
I know. It says the derivative is positive when x is less than 1. I know, it's hard to read this. That's the practice you need to practice. Practice reading this. Do these other problems, 69, 71, 72, and work on this one again. And you try to read this, and what this is telling you, when it talks about the derivative, it's telling you about increasing and decreasing. When it talks about the second derivative, it's telling you about concavity. And just use your number lines to help you. Yeah. Yep. I want to do another one. You know, one thing we haven't done, I'm going to back up. I'm in 4-4. I'm just trying to do good homework problems. One thing I haven't done as much is this second derivative test. They asked me to do it in the homework. Let me try. Let me try this 41. This looks good. 41 in section 4.4 is a function. This is a good looking function. I like this. X to the 2/3 plus 3. Is that what it says? Sorry. Minus 3. Sorry. Minus 3. All right, so what does it say? It says, find the relative extrema. Okay, you know what that means. Mins and maxes. And usually I use a first derivative test to do that. They're asking me to do a second derivative test is what they're asking for. But anyway, whether you're going to do a first derivative test or a second derivative test, if you want extrema, you need critical numbers, which means you need the derivative, and you need critical numbers. So here we go. I'm looking for critical numbers. This derivative is pretty easy. You guys know the answer? 2/3 x to the negative 1/3, and we're done. Wow. The derivative's done. The derivative is over. I would like to put that x to the negative 1/3 down into the denominator. So it's 2/3 x to the 1/3. And this is my derivative, and I want to ask these two questions. When is this derivative 0? Never. When is this derivative undefined?
0.
At x equals 0. You guys okay? When is it 0? Never. When is it undefined? When x is 0. Okay, you got to ask both those questions to get a critical number. So now I think we just found a critical number. X equals 0 is a critical number. Now, if I wanted to prove if he's a min or a max, I guess I could do the first derivative test and, do my number line. But they are asking me to do a second derivative test, and I haven't done much of that. So I wanted to remind you of how you do that. Do you remember what to do for a second derivative test?
The second derivative.
You take the second derivative, first of all, good job. And then you take your critical number from your first derivative and plug it into your second derivative. It's kind of funny. And then what's the deal? If it comes out positive, I think it's a min. If it comes out negative, it's a max. I remember that because if the second derivative is positive, listen, if the second derivative is positive, it's concave up. So now I know that my critical number that lives there must be a min. If my second derivative is negative, it's concave down. So I know that my critical number that lives in there must be a max. Anyway, I need my second derivative, and I will test this number by plugging it into the second derivative. Actually, I don't think this problem works. Watch this. What happens when you get your second derivative? What is the second? Well, sorry. To do a second derivative, I'm going to get back to this. Is that okay with you? And the second derivative would be negative 2/9 x to the negative 4/3. When you subtract 1. This is a negative 2 over 9 x to the 4/3. This is interesting. This is not the best example. What do I want to? This is a terrible example. What do I want to do? I want to plug my critical number into this second derivative. What happens when you plug a critical number into this second derivative? This particular example, when you try to plug 0 into here, what do you get? You get undefined. Okay, that's no good. I mean, that's no good, right? or no good, it's inconclusive. If the second derivative is positive, I know what to say. If the second derivative is negative, I know what to say. If it's undefined, it's inconclusive. I got nothing to say. The second derivative test actually failed. So what? Now I'm left hanging. The second derivative test failed. I guess I'm not totally left hanging. If I want to figure out if he's a min or a max, I could go back to the first derivative test. That is probably why their directions say, use the second derivative test where applicable. And it didn't apply too well to this problem. Sorry. Yes, Carlos?
What is the difference between a concavity test and a second derivative test?
That's a good question. That'll take me a while to answer that. Hold on to that. I'll get to that maybe. But in a quick question, in a quick answer, the second derivative test does not really, the second derivative test is testing critical numbers to see if they're a min or a max. The concavity test is testing your function to see if it's concave up or concave down. I mean, that's the answer to your question. What's the difference between the second derivative test and the concavity test? The concavity test is testing the function to see if it's concave up or concave down. The second derivative test is testing your critical numbers to see if they're mins or maxes, which I already have a test for called the first derivative test. But the second derivative test also does that in a different way. Hey, it failed here though. This second derivative test failed right here.
How did it fail? Because it was undefined.
Yeah, it's not positive or negative. If it's positive, I know it's a min. If it's negative, I know it's a max. It's undefined, I don't know nothing. Hey, you want to let's try a first derivative test then. You know, so I was trying to do a second derivative test on this 41. Listen, I think I'm going to do something here. I'm going to keep working on this 41 and adapt it to what I want to do. You ready? The second derivative test failed. Let's do a first derivative test. So what do? We put the critical number on here and we test around it. Let's try a 1, you guys. If I try a 1, where do I plug it? Where am I doing? In the first derivative, I plug in a 1. I take the cube root of 1. Positive, it's positive, everything's positive? It's positive. The graph is increasing. Let's try a negative 1, you guys. Let's try a negative 1. Negative 1. The cube root of negative 1. That's negative. That's negative. Divided into it, that's negative. It's decreasing. Okay, I find using the first derivative test, he's a min. You guys okay? Hey, let's look for inflection points since we went to the trouble of doing a second derivative. Look at this second derivative. When is it equal to 0? When is this second derivative equal to 0? Never. When is the second derivative undefined?
0.
At x equals 0. So I think x equals 0 is probably a possible inflection point. Are you guys okay? This is my second derivative. I'm going to put it on a number line. And this is an f double prime number line. And I'm going to test around this. Doing this test is not a second derivative test, right? Doing this test is a concavity test. I know it uses the second derivative, but it's called the concavity test. All right, let's try a 1. Where am I plugging this one? Where am I plugging it? Into the second derivative. And that's the cube root of 1. 1. Raised to the 4th.
1.
It's positive, but that numerator is negative. I think it's negative, which means it's concave down. The function's concave down. Check this out. Try a negative 1. The cube root of negative 1 is negative 1, but when you raise it to the 4th, it's positive 1. So it's positive. That's negative. It's negative again. So it's still concave down. So is this an inflection point? No, it's not an inflection point. It's not. Okay, no inflection. I guess I got no inflection points. He's a possible inflection point, but when I tested him, he's not really an inflection point. No inflection points. Huh, okay.
You have an inflection point on a minimum value.
I guess that doesn't make, maybe that you're right. That doesn't seem like that could happen. You're right. Well, you guys, you know what I want to do now? I want to sketch this graph. Again, I'm taking this problem 41 a little further than the book. Remember, the book wanted a second derivative test. That failed a long time ago. I'm going a little further. I'm exploring the first derivative test. I explored the concavity test, and now I want a graph, which is kind of the theme of this chapter. Take a function and analyze the hell out of it, you know? I mean, but here it is, you guys. This is so beautiful. This is awesome. When I plot this point, I want to plot this point. Or by the way, remember, I usually ask this. What are the relative mins? What are the relative maxes? And what are the inflection points? I usually kind of have a place for you to tell me this stuff. And I like to plot this point. What did we find? Oh, we did find a relative min, huh? We found a relative min when x is 0. If you plug that in the original function, what do you get for a y value?
-3.
You get -3, okay. So that's 0, -3. And that's a real live min. What about, did we have any maxes? Nope. Did we have any, nope. All right, I'm going to try to read these graphs and see what this does. What does it do? It decreases concave down. And then it hits this min, and then it increases. And it remains concave down. It's concave down the whole time, I guess. Okay, hang on. Decreasing concave down. How do I draw decreasing concave down? Like that. And now what does it do now? Increases concave down. Well, look at that. That's a beautiful function. That is a beautiful function. It's got one of these sharp points. Instead of a, you know, you can tell that this derivative, hang on, that critical number, that min, look at that critical number. Did that critical number come from the derivative being 0?
No.
If it would have, that's a horizontal tangent line, right? When the derivative is 0, we don't have one of those. It's that other kind of critical number. This critical number came from the derivative being undefined, which is maybe a sharp point kind of critical number. Cool. That was fun. That happens with these x to the 2/3. Is you get that beautiful cusp. Let's try another one. Let's try number 40. I'm in section 4.4. I want to do this second derivative test. It didn't go too well on that one. It failed me here. Let's try it. Let's try this one. Negative x to the 4th plus 4x cubed plus 8x squared. Negative x to the 4th plus 4x cubed plus 8x squared. This is my function, number 40. And I'm looking for mins and maxes, critical numbers. I need a derivative. The first derivative is negative 4x cubed plus 12x squared plus 16x. I want to set it equal to 0 and look for my critical numbers. When I set it equal to 0, I think I'll factor out a 4x or a negative 4x. Is that okay with you? What am I left with? X squared minus 3x minus 4. I took the derivative. I factored out a 4x. This is smart. It's good to be good at algebra. It's good to be good at algebra. This factors nicely. X minus 4x plus 1, I think. I think I got my derivative all factored. So my critical numbers are what are they? 4, negative 1, and 0. Yeah, when you set those factors equal to 0, that's what you get. Cool. I got 3 critical numbers. I want to test them to see who's a min or a max or a neither, a min or a max or maybe a neither. In order to test them, I kind of prefer a first derivative test, but I'm trying to do what the book said. They want me to do a second derivative test. Let's try it. A second derivative test means I need a second derivative. That's not hard on this one. A second derivative is kind of easy here. Second derivative. Negative 12x squared, you guys with me? Plus 24x plus 16. And now to do a second derivative test, I take those critical numbers from the first derivative and I plug them into this second derivative. So I want to check out what's f double prime of 4. I want to see what's f double prime of negative 1. And I want to try f double prime of 0. I want to plug the critical numbers from the first derivative into the second derivative. If it's positive or negative, I'll learn whether these are mins and maxes. That's the game. All right, I'll try it. Plug a 4 in there.
It didn't work today.
I ran out of batteries. Plug a 4 in there. I think it's negative. Negative 80?
Yeah.
Negative 80. Anyway, it's negative. When the second derivative is negative at a critical number, that means that critical number is a max. Let's try negative 1. I'll plug negative 1 in there. I think that's negative.
You plug in negative 1, you get negative 20.
Negative 20? So it's negative. I don't really care about the number, but it's okay. It's negative, which means he's a max, huh? That means he's a max. All right. If I plug in a 0, I can do that one. If you plug in a 0, you get 16. And that is a positive, and if it's positive, it's a min. This x equals 0 must be a relative min. I didn't really want to go sketch all the graph and everything, but I mean, I kind of want to just stop it there, except for one, I want to add this. You know, I mean, sometimes, I mean, there's stuff you know, and you do have your graphing calculators that can help, but there is some stuff you know. I mean, I don't want to do a whole analysis like I did last time. I just want to say, you know, this is a 4th degree polynomial. You know, when I teach college algebra, I teach them that a 4th degree polynomial, both ends go up. The end behavior is up, except then it has these hoops and loops and stuff. You know, polynomials are beautiful. Anyway, it has mins and maxes and so forth. But anyway, both ends are up, but wait a minute, not when that's negative. Then both ends are down. So I've got both ends down, and I did find, when I did this work here, I found 2 maxes and a min. So I'm just very roughly, I'm saying I got 2 maxes and a min. And I got a 4th degree, upside down 4th degree polynomial. I mean, I don't know, I'm just recalling my algebra, and I know a lot of stuff if I recall my algebra. Anyway, that's very rough. But at -1 there was a max, at 0 there was a min, and at 4 there was a max. But whatever, just very roughly. Let's try another problem. I like doing all this homework. Check out this 79. Did you guys try this one in 4-4? This might be tricky. Let's see what it says. In 79, it says a small aircraft starts its descent at an altitude of 1 mile, 4 miles west of the runway. They give me this cool picture, which is nice of them. They're saying there's an aircraft over here. That's an aircraft. And it begins 4 miles west of the runway. They call this the runway where he wants to land. And he's got a 1 mile altitude, I think it said. Yeah, he's 1 mile up. He's 4 miles west of the runway. That's an airplane. Or a mosquito, whatever you prefer. And they got this path. See, he needs to, I've never flown airplanes, maybe some of you, but you need to come in here. You can't do this. That doesn't work, I guess, right? It's kind of rough on the passengers. So you kind of got to switch concavity. Look, you kind of got to switch concavity to come in with a smooth landing, you know? So they drew that flight path for me. And what are they suggesting? What is their question? Wow, they say find the cubic function that describes the smooth path for this landing. They want me to find the cubic function, and so they said that this is some cubic function, f of x, and here's what a cubic function is. It's an ax cubed plus a bx squared plus a cx plus a d. Oh my God, they want me to find this. And to find this means find a, b, c, and d is what that means. Wow, that's a good problem. All right, so what do we know? Let's see. I don't know. What do you guys? Do you know anything? What do you know? You do know some points. Thank you. You know some points. Like, you know it's going to touch the point 0, 0. So that means if you plug a 0 in for x, what's the y value going to be? 0. Now, you know what? If I go ahead and do that real quickly, watch this. If I do plug a 0 in for x, I plug in a 0 for x, guess what I get? If I plug a 0 in for x, I get d. And what am I supposed to set it equal to? The y value, which is 0. I'm plugging in a 0 for x, and the y value is 0. When I do that, the y value is 0. I plug in a 0 for x, and all of a sudden I just learned that d is 0. Is that okay with you? I plugged my point into the function, and I discovered that d was 0. Yes, Carlos?
What was the reason for plugging in 0?
Because it goes through that point. And going through that point will help me find, yeah, that was awesome. Do you know another point that it goes through?
Negative 4, 1.
Negative 4, 1. It does, right? See it? It's kind of where it starts, I guess. It starts at negative 4, 1. So when x is negative 4, the y value is 1. I'll try that. That means if I plug that in there, the y value is 1. I plug in a negative 4 for x. What do I get? Negative 64a. You guys okay with that? Negative 4 cubed times a. I'm plugging negative 4 in for x. That's 16b. And a negative 4 for x, that's negative 4c. I already know d is 0, so I'm not going to put d in there. All right, well, that's cool, but I can't find a, b, c. I mean, when I got one equation and 3 unknowns, I'm kind of stuck. I need some more information. Can you see any other cool information? Well, we could talk about concavity. How about between a function and concavity, what is there? The first derivative. What can you say about the first derivative? What can you say about slope?
Negative.
Yeah. How about, what can you say about some certain slopes at certain places? What can you say?
Oh,
I think when it starts here, it's got a nice level flight path. So what's his slope? His slope is 0. Thank you. So hang on. At -4, his slope is 0. How do you write that? F prime of -4. At -4, the derivative is 0. Is that what we're saying? It's got a slope of 0. Is there another place where that happens? When it lands. Thank you. I think when it lands, we want the slope to be 0 to make a nice smooth landing. So in other words, F prime of 0 equals 0. So that was cool, you guys. Look, in this picture, there was what I saw, and I saw it early, but I tried to coax you there. Listen, I saw 2 points, and I just described 2 points. But at those 2 points, there was something else going on. At those 2 points, the derivative is 0. The slope is 0. This is going to help me a lot. Listen, let's go back to this. Can you please take a derivative of this? The variable is x. A, B, C, and D are numbers. You can do a derivative. It's
3ax squared.
3ax squared. Good. 2bx and c. That's the derivative. Hang on. So what did we just say? I'm going to go over here. If you plug a 0 in the derivative, you get 0. Okay, I'm going to do that. If you plug a 0 in the derivative, you get 0. If you plug a 0 in the derivative, you get c. And it's supposed to equal 0. So I think we just learned that c equals 0. That's awesome. By the way, that means I can go up here and say, this c is 0. What does this say? If you plug -4 in the derivative, you get 0. That's the 2 ideas we had because those slopes were 0. So if I plug -4 into the derivative, you get 0. Okay, this will be a 0. And I'm plugging -4 into the derivative. That's 16 times 3, that's 48a. Plugging a -4 in the derivative, right? Plugging a -4 in the derivative. That's -8b. Oh, and plus c, but remember we knew c was 0. We had c was 0. Hey, you guys, that's it. This was a funny little word problem, but I dug out those 4 important facts and I plugged them into this generic function. And what I got now is I got 2 equations, 2 unknowns. I got an equation here with an a and a b. I got an equation up here with an a and a b. With 2 equations, 2 unknowns. You can go back to 3rd grade and solve this. Maybe 5th grade. 2 equations, 2 unknowns. You can find a and b. I'll help you. On your mark, get set, go. I'm moving the 8b over here. 8b equals 48a. Divided by 8b is 6a. Hold that thought. What do you do with that thought? You take that b. By the way, my b's look like 6's. Be careful. I take that b and I go plug it in up there. Up there it says 1 equals -64a plus 16b. But what am I plugging in for b? A 6a. Thank you. A 6a. So that's a -64a. That's a 96a. When you add that, that's 32a. That equals 1. So guess what a is? 1/32. If you plug that 1/32 in here, you get b. b is 6/32 or 3/16. This is awesome. I love these kind of problems. So, I mean, the question was, can you find this cubic function? And we just did. We found the cubic function that's going to meet their requirements. Here it is. It's this cubic function with the a, b, c, and d filled in. 1/32 x cubed and 3/16 x squared. And if you remember, the c and the d were both 0, so this is it. This cubic function looks just like this. And it meets all these requirements. It's got a slope of 0 right there. It makes the airplane fly in here beautifully, land beautifully. Now the whole time the pilot was calculating all this, you know, he probably just overshot his airport. So now he's got to recalculate everything. Maybe he had a computer that calculated all this for him. That was a good problem, you guys. That was 79. I love trying to find. There's a couple kind of like that before it. It's not an aircraft trying to land, but it's a similar. 77 and 78 are similar. They could be a little tough. Okay, listen. I'm moving on here. I'm going to 4.5. In 4.5, the title is Limits at Infinity. And I just want to show you, I don't think I assigned a whole lot of these problems. We can revisit these limits later in Cal 2. The limit as x goes to infinity of 3x over x squared plus 1. So it's been a while since we've done any limits. I just made up a limit problem. Do you remember step 1 of doing limits? Plug it in. What's kind of funny is plugging in infinity is a little funny, but we can try it. Listen, if I plug in infinity, I get 3 times infinity. 3 times infinity is infinity. You don't have to think about it too long, maybe. And now, in the denominator, I get infinity squared plus 1. Let's see, infinity squared would be infinity. Well, what about if you add 1? All right, infinity. So the numerator and denominator are both infinity, and technically, these can be very difficult limits. Sometimes they need a lot of difficult work. They're called indeterminate. When you have infinity over infinity, it could lead to a lot of different answers. This is called an indeterminate form. Yes, Carlos?
Is that pretty much the same concept as before when we were doing these types of problems in chapter 2 when you plugged it into the equation and you ended up with 0 over 0 and you had to fix it?
You know, you're kind of right. It is a similar concept. 0 over 0 was also an indeterminate form, yes. 0 over 0 is a famous indeterminate form, and back in chapter 2 we had ways of fixing it. He's exactly right. And now this is new though. Back in chapter 2, I don't think we ever ran into any infinities over infinities. So this is a new indeterminate form. You're right. And in a way, you know, I don't know, man. The book teaches you a technique on actually how to do this. And I don't like that technique in particular because I know one thing, because coming up in Cal 2, we learn better techniques. So I kind of don't like their technique. I would really like to resort to logic here. And maybe though, but this might be a totally new concept for you. Listen, these are 2 different types of infinities. Maybe you think infinity is infinity, but these are 2 different types of infinities. I want to say one's a bigger infinity than the other one. Which one's the bigger infinity? The infinity squared is bigger than the regular infinity. Is that okay with you? And therefore, I'm just going to, the way I like to do this, I'm trying to do this kind of as a more logical algebraic approach. And I want to just say that denominator is a bigger infinity. And if the denominator is a bigger infinity, and when you have a denominator that's blowing up faster than your numerator, what does the fraction do when the denominator is huge?
Closer and closer to 0.
The fraction goes to 0. When your denominator is huge, the quantity goes to 0. You can just. And so because this is a bigger infinity in the denominator, I'm just using logic and saying the answer is 0. The answer to this limit is 0. Yes.
What did you just do there? I didn't quite the last part.
The power on the x made it an x squared, and this was just an x to the first. And when I plugged in infinity, the infinity squared is bigger than infinity to the first. Infinity squared is bigger than infinity to the first. So the denominator goes to infinity quicker than the numerator. And therefore, when the denominator goes to infinity quicker, and when the denominator wins, the whole fraction goes to 0. See, that part shouldn't be... You should know that. When you have a fraction whose denominator blows up, it goes to 0. Is that okay? That should be kind of clear. A fraction whose denominator blows up to infinity, that fraction goes to 0. Okay, what about this one? Step 1 of doing limits. Plug in infinity and see what you get. Okay, you plug in infinity in the numerator, you get infinity cubed. I'm just going to call infinity cubed infinity. In the denominator, you get infinity squared plus 1. Guess what that is? I'm calling that infinity. So really, it's this infinity over infinity, but if I think about the powers that I just dealt with there, I would say the numerator is a bigger infinity now, right? It's infinity cubed. That beats infinity squared. Is that okay with you? I want to call this a bigger infinity. Well, that means the numerator blows up to infinity faster than the denominator. So what does the fraction do? I think it goes to infinity. It goes to infinity. Well, the numerator's a bigger infinity. I mean, you can, listen, this is terrible, sloppy math. I should hit pause and never show this on the recording. But you can kind of think of it as infinity cubed over infinity squared, and you cancel a couple of infinities and you get infinity. You can kind of think like that. Don't tell anybody though. It's comparing the sizes of these infinities, or who's going to infinity quicker. Maybe it's not the size of the infinity, but the rate at which it goes to infinity. That'd be an appropriate way to talk. What about this? The limit as x goes to infinity of this guy. 4x squared minus 3x plus 7 over 3x squared minus 41. This is a good problem. Step 1 of doing any limit is you plug in infinity. If you plug in infinity, you get infinity squared times 4 minus 3. Anyway, I think the numerator is infinity. I think the denominator is, listen, it's infinity squared times 3. Even though you subtract 1741, still down, still infinity, right? Right, it's infinity. So it's infinity over infinity. This time, who wins? And what you should realize is that you don't need to pay you don't need to pay attention to these other terms. It's all dictated by these leading terms. And in this case, it's a tie. And it's sort of a tie. And so it's sort of 4 of those infinities over 3 of those infinities. The answer to this one is the ratio of those infinities. The answer to this problem is an actual number. 4/3. So now, I just did 3 good problems for you. I know sometimes I'm organized today, okay? Sometimes I'm less organized. Today I'm more organized. These are 3 good problems. 3 good problems, and we just went through all 3 scenarios. I mean, these are the 3 scenarios. When you have infinity over infinity, what are the 3 scenarios? The denominator is a bigger infinity, which makes it go to 0. The numerator is a bigger infinity, which makes it go to infinity. Or they kind of go to infinity at the same rate. They're sort of the same size infinity, which means it's the ratio of those leading coefficients. You with me? So it's about this leading power is kind of what it's all about. An x to the first over x squared, an x cubed over x squared, 2x squareds with leading coefficients. Now, so that's the story of these limits. But the truth is, when it comes to this quiz or this test, I don't think I'm going to ask you one limit question. But you know what I am interested in? Do you know about your horizontal asymptotes? Well, this is just a horizontal asymptote discussion, actually. I mean, that's what this is. Let's talk about it like that. Listen, the other day we talked about horizontal asymptotes. I didn't really totally write down all the rules, but maybe you recall that when the numerator is a lesser degree than the denominator, when it's a lesser degree in the numerator, there's automatically a horizontal asymptote at y equals 0. That's why this function approaches 0. When x approaches infinity, this function, when x approaches infinity, this function is approaching 0. That's what this says. This is a calculus way of saying you got a horizontal asymptote at y equals 0. Are you with me? I'm trying to make that connection. That's the connection I want to make. That these limits they're fun little limits, but they're really trying to get me to think about horizontal asymptotes. Here's one. When the numerator has a higher degree, do you remember your horizontal asymptote story when your numerator has a higher degree? Do you remember the story? From pre-calculus or college algebra, the horizontal asymptote when your numerator has a higher degree. There ain't one. There ain't no horizontal asymptote. There ain't no horizontal asymptote. What there is there's a slanted asymptote, perhaps. An oblique asymptote, they call it. And if you had an oblique asymptote, what would your function do? I think it would head toward infinity. I mean, it's a horizontal asymptote that makes it head toward a number. If you've got a slanted asymptote, then your graph is going to head toward infinity. Are you with me? I'm trying to connect the calculus of this limit to the algebra of asymptotes. And so let me just say there is no horizontal asymptote. This graph approaches infinity. No horizontal asymptote. There is a slanted asymptote or an oblique asymptote. I don't really care too much about those, but it's not horizontal. Hey, what about this one? Do you remember the rules of horizontal asymptotes when the degree of the numerator and the degree of the denominator are the same? Yes, I remember those rules. When they have the same degree, the horizontal asymptote is y equals the ratio of leading coefficients. So, and that's the answer to this limit. As x goes to infinity, we're approaching an asymptote at 4/3, apparently. All right, good. So, I took you through some homework, 4.3, 4.4, and 4.5. I just want these ideas about asymptotes. I'm really not going to ask you limit questions. You can try a little bit of homework in 4.5, but it's focused more on what are the asymptotes. All right, so I quit today. Thank you.
Me too.
I'll see you tomorrow, or not tomorrow. If you got questions, come see me, but I'll take questions from you Friday.